Welcome back to Meteorology 101. In this video, I'm going to talk about surface charts, upper air charts. Just going to do some analysis. I got a program I can download the latest METAR data and upper air data from radio sondes, weather balloons, and this program analyzes the charts based on pressure, temperature, winds. We can break down the upper levels and see what's going on with these systems. So right now I got a backdrop on the map. It's the latest radar. It's just one single shot. It's the latest radar image. It's not a loop, so this one doesn't do loops as it analyzes those charts. So we're going to use this for the surface. Once I get up into the upper levels, the 850 millibar, 700, then we have to go to a blank white background on the map, just because of the way the colors interfere with each other. I got moisture on the upper levels that will show that this program will analyze also, and then that green overlying on this radar just doesn't look right. So we'll just change the map when we get there. So right now, I know we got a current weather system over the eastern United States. That's the low pressure system. Developed over Texas, moved to the east, and then moved to the northeast, and staying on the eastern side of those mountains. And then any upslope flow or moisture being pumped in from the ocean, any onshore flow, pretty much where we got our moisture. We'll see how far the moisture goes up, how deep this low goes, and try to analyze that thing in the upper levels. Lee side of the mountains, lee side of the Rockies, looks like we had maybe a lee side trough. We got some troughing going on in the central United States, and then maybe a plateau high on the typical weather pattern, bringing moisture in from the northwest and then wrapping moisture around into Oregon and Nevada. Let's go ahead and do our pressure chart. We'll see what we got. Right now, I'll do the station plots. So the station plots can tell us quite a bit. Pressure, winds, temperature, dew points, and types of clouds. I mean, depending on what that weather observer puts into that system, what this surface plot is going to show. Now, right off the back here, we got all the blue. We got red. You see the red, blue, and the black plots. So the red plots are IFR conditions, which visibility is less than 1 mile, or the ceiling is less than 1,000 feet. The blue is marginal VFR, which is the ceilings are anywhere from 1,000 to 3,000 feet, or visibility is 1 to 3 miles. And then the black plots are just VFR conditions. That means the ceiling's above 3,000 feet and the visibility is above 3,000 feet. So just based on this, you can see where the radar is, the precipitation on the radar. Looks like light snow there according to that weather symbol at that weather station. And then getting up into the mountains, you get the lower ceilings. Ceilings are less than 1,000 feet, and then between 1,000 and 3,000 feet on the west side of the mountains, and then to the south. So you can see how that system is affecting the lower cloud base, and then what type of precipitation is associated with that system. Now, if you look at the wind direction, you can see like the winds out of, I think that's Tennessee, out of the north, and then we're shifting to the northwest. Here's one off the coast out of Bowie going to from the northeast, one from the southwest. So maybe some rotation there if that one's accurate. Some of them buoys out there get quite a bit of wind shifts out over the ocean sometimes, so you got to take some of that with a grain of salt. So the wind directions, I see some rotation here. We may be the low pressure system over the east coast. We'll go ahead and lay our sea level pressure out. This will be the ISO bars, lines of equal pressure. So the computer will analyze all the pressure readings on this chart and place those lines of equal pressure. So on the top right hand corner of the station plots, you have a number like 269. That's 1026.9 millibars. and then, like I said, the computers will analyze that to give us our pressure systems. Then we'll be able to see the highs and lows. So let's go ahead. Well, I just hit the temperature. But these are isotherms, lines of equal temperature. So on the station plot, the top number, there's a good example there, 40. And the top number is temperature. It's 40 degrees. The bottom number is the dew point, which is 30 degrees. So you have a 10-degree difference. Once we get up to the upper levels, it reads a little bit different. I'll show you what I mean by that. But right now we have the isotherms, lines of equal temperature, and you can see the temperature gradient from the north to the south. So you've got a pretty good idea where your jet stream is through there. We'll pull up a thickness chart, and that'll be 1,000 to 500 millibar thickness. That basically shows you what the thickness of the atmosphere is between 1,000 and 500 millibars. So you get a better idea for jet stream placement, frontal placement, a lot of stuff the thickness chart could tell you. So right now we're on the surface. I'm going to do the lines of equal pressure, the isobars now. So okay, we've got low pressure over the Atlantic, a little bit off coast. So right there was that rotation. The wind's out of the northeast and then out of the southwest, so there is definitely some rotation there. And then you have the onshore flow. The wind flows counterclockwise around the low, so any moisture that's wrapping around this low pressure system is just going to push onshore, feed that system, and then any lift that we can get from the land, the mountains, anything like that will help give the more precipitation, push the moisture in the upper levels, and then help intensify this system. But right now if we had to place a front, probably would be out of this low pressure system. A little hard to tell on any major wind shifts. We got some wind shifting right here out of the west and the northwest. So I don't post every plot across the United States, because this map will be so full you won't even be able to read it. But I do it like 85% of the plots. The round stations are actually where an observer walks out and does an hourly weather observation and submits that to the National Weather Service, and then these charts are developed. So the square weather stations are automated surface observation systems. The ASOS, it's a weather station that sits out there, and that actually shoots a beam up and then measures the cloud height and tries to get a picture of the sky. If there's one cloud right above that ASOS, it's going to say overcast. So you got to go with a grain of salt on that too, being the automated system. But the winds and the temperatures, dew points, all that's pretty accurate on these things. They go out, they just transmit data every hour automatically into the system to just give us a better understanding on these charts. So when the dot or the square is colored in solid, that means it's overcast skies. The blue one here, if you see that one, it's 3/4 of the way filled in. That means the skies are broken. It's still a ceiling. If they're clear, it means clear skies. If it's cut in half, just split right down the middle, that's scattered cloud sky condition. And then if you have 1/4 of that corner filled, then it's a partly cloudy. It's few. So this is a surface chart. I'm going to do, I'll erase this and get rid of these highs and lows, because when I put fronts on here, it puts the highs and lows, and then that kind of makes it pretty cluttered. So it's a computer generated fronts, and you got to take those with a grain of salt too. That's why it's important to be able to read these station plots and see exactly where these low pressure systems are, see where your fronts are, where your temperature gradients are, so you can analyze that data down to a much better level and get a more detailed forecast, more detailed information on what's happening with that system. So this low pressure system was over Alabama yesterday, so it's continuing to move to the east. So if you look at if the jet stream's in this tight temperature gradient, then it's going to pretty much, that's your steering pattern. That's where that low pressure is going to head to. So let's get a look at this, these surface fronts. Let me go with, I think I put the pressure last. I can just remove that one. And then we can go add the pressure without the highs and lows. Now we still see our isobars, no H's and L's on there. So when we place our fronts, it's not so crowded. Alright, so here's the fronts. Okay, so that front, being out in the ocean, the computer's just kind of extrapolating where it thinks that front should be. The warm front, cold front. Okay, with that low pressure system having a closed low, and really not any other isobars in there, how much flow do you actually have, and how tight would that be? You know, you got 1,004 millibars, so it's not like a real deep system. So I would probably put this front, looking at the wind shifts, let's see, look at temperature, 74 and 65. So I would bring that front right between there. The warm sector being 74 degrees, then the cold air behind it being 65. There's a 57, so probably right through that 65 be a good place for that cold front, just based on this temperature advection. The wind's coming out of the north, pushing all that cold air to the south, and with that temperature advection, that'd be the leading edge of that cold front. So low pressure over the northwest, showing another frontal system there. I'm not sure if I agree with that. I don't see a lot of, there's maybe a little bit of temperature advection there, but nowhere near where that front should be placed. And then it's going stationary out of that low, high pressure. See, it just throws H's, L's wherever it wants in here. So it's just kind of, it's pretty scattered. That's why you got to analyze this stuff. Look at like lee side of the mountains. Look for this rotation. Is there any rotation around that low? You definitely have trophied on lee side of the mountains. Maybe in a little area of high pressure, that's showing 1,028 millibars right there on a closed high, the plateau high. I mean, if this is the high pressure system, that's just not, like I said, this thing's so scattered. The surface chart is just not jiving too good right now. So going to lower pressure toward that low. So that's still baroclinic. We have the isotherms crossing the isobars, so we still have a baroclinic system there. If we had more data over the ocean, we could tell, you know, where that front would be. I'd just place it right into this, right into that trough. You can actually see a wind shift right there. So this frontal system, bring it down, and then maybe connect into this system, going a little bit stationary, and then tying into that system, and then wrapping that front back around from the cold front. So that'd be my first initial guess on it. And high pressure with a bunch of troughing through the central United States, probably causing that precip on the east side of the mountains. Basically a lee side low that just caused just enough lift from maybe some cold air dropping off the mountains, compressing, warming, and giving a little bit of mixing right there to create some of that moisture. You create some of them that precipitation. So alright, that's pretty much it for the surface chart. Let's go with the 850. Let's go up one level. Actually, let's create a thickness chart. Let's see where we're at there, so we can place this jet stream, see what kind of jet support this low pressure system has. We'll shoot up to the 300 millibar, get a good look at the jet, maybe 250 or 200 millibar also. So we'll go up over 30,000 feet with these charts and see what we got. We run a script. I got I hit the station plus. Let me erase that. Okay. This program will run scripts. Let's do a 1,000 to 500 millibar chart. Where are we at here? And then we'll automatically build these charts for me, so I don't have to go in and pull every parameter and load every different detail. I got scripts written, into the program. I can just run that script and it will load everything for me. So basically the same thing, the isobars, the station plots. Now with the thickness lines, they're a little bit hard to see on this colored chart, but you can see these red dash lines. Those are heights at 500 millibars. Shows you the thickness where you have ridging, higher heights on the west coast, troughing over the central United States, and then basically still just that trough extends all the way over to the eastern United States. So you have lower heights. So that indicates just the low pressure over the east coast, high pressure over the west coast. So now the main thing about this thickness chart is the 540 line. It's 5,400 meters. That's I color that one purple. That's the mixing line that any precipitation. This thing curves around pretty tight. Any precipitation to the north of that 540 line is going to be snow. Any precipitation to the south of that line is going to be rain. And any precipitation along that line is going to be mixed. So it'll be rain and snow mixed. And then depending on your freezing levels, how thick your cold layers are, any warm layers in the upper atmosphere, how thick they are. You can have a cold layer, warm layer, cold layer, and then the precipitation fall out of that cold layer is frozen precipitation, fall through a warm layer, partially thaw out, defrost, and then it will fall through that cold layer and refreeze. And then depending on the thickness and the levels, if it completely refreezes, partially refreezes, stays a liquid till it impacts the surface and then causes freezing rain. There's a lot to that too. So this is just your initial, with the 540 line, that's your initial guess on, okay, that area is going to be a mixed precipitation anywhere along that line. Anything south is rain, anything north is snow. So, all right, that low pressure system now is over the Atlantic, right off the East Coast. Let's keep an eye on where that center was, because what we're going to look for in the upper levels, we're going to look for a tilt. If we have any stacking into the upper levels, typically these low pressure systems will tilt toward the colder air. And then with the jet support, it's like blowing an air hose over a tube. It will create a suction, and that jet stream will just suck the air mass out of that low pressure system and actually cause it to deepen. So keep an eye on where that is off of the East Coast, right there off the East Coast of North and South Carolina. And then we'll check out what's doing at 850 millibars. Let's go ahead and pull my 850 millibar chart. Now I'm going to run some script on this one. This first, that's going to be the moisture. Well, like I said, we need to get rid of this chart first because it's not going to show up very good on this thing. So I'm going to just recenter. Alright, that should get us where we need to be. Probably go a little bit higher here, get this more centered. Alright, so now we can run our script for the 850 millibar. First we're running moisture. Alright, so we have significant moisture throughout the United States, that right pretty much just diagonal. So let's go ahead and put our pressure up here. 850 millibar height. Now that low pressure just shot back back into inland. So our low pressure was way out here. That'd be a pretty strong stack if that was the case. So we've seen those wind shifts on the surface where that low pressure was, so it kind of indicated where that low was, but that is pretty strong stack. I mean, this system wouldn't be, I'd like to see a little bit less stacked than that, but not vertical. If you go vertical, then it just becomes a barotropic system and be a slow moving system. This system, it could be that stacked, I mean, that far back, and then that might explain why this is kind of a weak system. I mean, it's creating a pretty good storm along the mountain range just on the east side of the mountains in North Carolina. I think they're looking for like 8 inches of snow there. If we get some time, we'll look at some forecast models on precipitation and see see what we're looking at there. Still high pressure over the mountains, and then there's a low pressure way over the northwest and then way over the northeast. So this is the main system we're looking at over the United States right now. Now, if we get any cold air advection or any, this should be a baroclinic system. Let's go ahead and throw our isotherms on there. Well, actually, let's get our station plots on there too. We want to see what's going on there. Actually, let me remove those real quick because I want to bump that up from that 85% plots to about a 99-100% on the plots. Because in the upper levels, there's only so many stations across the United States that let the weather balloons go, the radiosondes, to get that data. So I want pretty much every one I can get that sends that data out every 12 hours. The mandatory levels they send out is 1,000 millibars. They'll send out 850, 700, 500, 300, 250, and 200. So that radiosonde, as it goes up into the atmosphere, as long as the balloon stays intact, it's sending back data at those levels. That's the mandatory levels that it's required to send back. It's programmed to send back. So winds, temperature, dew point. All right, so if you've ever seen a SCOOT chart, then you can see one station, what the atmosphere structure is in the vertical at one location. Basically, that's what these charts are doing. They're taking that data from each one of these locations, the dew point, temperature, and dew point. But see now this dew point, the difference here was this is 0 degrees. I'm right over Montana. 0 degrees temperature Celsius, and then the 4 is a dew point depression. So that's the difference between the temperature and the dew point. So basically, you're -4 on the dew point because the dew point's always a lower temperature than the air temperature. So anything that is a 5 dew point depression of 5 or less is considered to be saturated, and you will have significant moisture. So that's what this computer program analyzes, that data, and anything that's within 5 degrees of each other, it paints green. So once it gets over the ocean, it just kind of throws a lot of color out there. So you got to kind of take that with a grain of salt. But we live on land, so we pay attention to all the data that is over land. Keep this, like I said, anything 5 degree dew point or less, any 5 degree difference or less is going to show saturation. So we are still baroclinic from the low pressure system. We're showing a wind from the northwest and then going more easterly, so we could probably say there's maybe an upper front right through that trough. This troughing on the low that place that front right up at the 850 millibar. So I have an upper front, so that's a pretty significant system. Looking at the isotherms, warm air advection starts to get a little weak right through the south of that low, and then the east of that low you have some weak advection, and then on the west side of that low it starts to pick up a little bit. So it's still a baroclinic system, still closed low, still a pretty decent system at the 850 millibar level. So you can pretty much count on clouds being all through anywhere this moisture is. All right, let's go to the 700. We'll run our script on moisture. So now we just dropped a lot of moisture at the 700 millibar. So 850 millibars are right around 4,800 feet, 5,000 feet. So just to give you an idea, 5,000 feet up where the moisture is, 700 millibars are right around 11,000 feet. So between 5 and 11,000, we've lost significant moisture throughout the United States. Still over North Carolina, Virginia, Kentucky, and Tennessee. So we do have a pretty good, moisture there. Anytime winds are going up against those mountains, being pretty high, you can push that moisture up to those levels, and maintain that. So as long as you have a wind perpendicular to the mountain range. And then, like I said, on the lee side of the Rockies, you still have significant moisture up over those mountains also. And let's go ahead and run our station plots. All right, so we're minus 11 with a 5-degree dew point depression. So for some reason the computer didn't catch those, probably because this one station has a 9-degree difference, so it kind of cut that out and it couldn't just wrap around the one and then the other. So it just the way it extrapolates that data. So you can take the moisture out over these areas just a little bit further, and that just still gives you, like I said, the significant moisture in those upper levels. Now if we run our pressure, see if we still have a closed low at 700 millibar. It actually didn't, it's not closed. It did stack back a little bit more. Let's go back, I want to go back to the 850 real quick. I'm going to overlay the 850 pressure just for a second, just to get an idea where that low, see where that low is and what kind of stack we have on that. So we did stack back just a little bit there, and then like I said, the surface was way out here, so big jump from the surface to the South Carolina, and then from there to Georgia. So this is a better stack right there. You have a stacked low pressure system, and then we knew we had jet support. So once that system gets pretty stacked, then you got a baroclinic system. It can be developed into a pretty strong system. So it's something to watch for as these systems develop. Like, you can get these lows, pressure systems develop over Colorado. Be a Colorado low, come down out of the mountains, create a lee side trough or lee side low, and then the jet stream pick it up, and then it could drop to the southeast and then curve back up with the jet stream and come up the east coast. Now, anytime that low pressure system develops over land, depending on what kind of moisture is available and how much onshore flow you might have from the Gulf, where it can get its moisture source to keep pumping into that low pressure system, what kind of system, how severe that weather is going to be, how much precipitation you're going to get. If this low pressure system develops over Texas, then it's closer to the Gulf. It can bring some of that Gulf moisture up, get some warm air advection ahead of that low, pump that moisture up on inland, and then pick that moisture up and move to the northeast, and then you can actually get a pretty decent storms through the eastern United States, especially in the wintertime, where that jet stream drops to the south, and then cold fronts extend from the northeast to the south and then become stationary, and then get a low pressure system develop along that frontal system, and then pick up that moisture and with the jet support and become a pretty strong system moving over the northeast. Let me get rid of this. Let me get rid of that. It's pretty crowded there. So, and then if that low pressure system was to develop over the Gulf, which doesn't happen a lot, but it can happen. Actually, 1993, that storm of the century, that was developed over the Gulf of Mexico, and that just brought all of that moisture. It was saturated and just brought it inland and up the east coast, and just dumped, just feet us tons of snow and ice, and the whole northeast was without power for quite some time. So actually, I do have, this program does have history data too. If I can figure out, I can't remember that date. Actually, I might have the chart saved from 1993. It was like March. We'll look at that low pressures if we got time. I'm coming up on 30 minutes already, so we got a long way to go in the upper levels. We probably won't get to the models. We probably won't get to any history data. I'll save that for a later date. But right now we're at 850 millibar. This is 700 millibar, and that's about 11,000 feet. We have a low pressure system, almost a closed system. I would probably say that could be a closed system just based on these winds. Winds out of the east. What's it got? Southeast, south, out of the east, and out of the north, and then out of the west. So here, that definitely is your rotation area. You're troughing right there, and then still significant enough to put a low pressure system there instead of just a trough. So that's probably about right. Not really closed at 11,000 feet. So if we go up to 500 millibars, about 18,000 feet, then we can see, let's get a good look at what type of moisture we have in those upper levels. Still got some moisture present. With the west coast, east coast, mostly north up West Virginia, Kentucky. So the moisture over North Carolina, where that low pressure system, the upper level low, 850 millibars, pushing any moisture up that mountain range. Anything at the surface is way out. So it's a little weak on that system. That thing weakened quite a bit overnight. Yesterday it was showing a pretty good system all the way up, closed low all the way up to 300 millibars. I mean, that was a pretty well developed system. Would have been pretty interesting if we had if it had the moisture to really go with it. A little bit tighter, a little bit deeper system, that could have been a real snowmaker there. I mean, don't get me wrong, it's still developed. I guess there's still snow falling over North Carolina, Virginia, so we're still, I think they're still counting the snow, so we'll see how all that ends up. So we're going to go with some pressure. This is at 500 millibars, about 18,000 feet. Let's pull 500 millibar level. That's a little light. Let me get rid of that one. I want to keep the darker color so you guys can see it better. Still got the low pressure showing up. That's over Tennessee. The troughing. Check out our isotherms, station plots. Still got significant moisture, low pressure, troughing. You can see the rotation of that system. And then now, without the isobars being closed off around this low, even over Ohio, Indiana, Kentucky, tri-state area, we're not looking for significant thermal advection. We just really don't have it. This system is weakened a lot, so if you look at the isotherms becoming more parallel with the isobars, these contours, the upper level pressure, that becomes more barotropic, and that just gives you an indication that the system is filling and getting a little weaker. So, and like I said, for last night, this was a pretty significant system. Closed low all the way up to 300 millibars. So it's actually opened up even all the way down to the 700 millibar level. So like I said, it's weakened quite a bit. Now you do have some moisture plots out here that are 5-degree dew point depression or less, so you still have a little bit of moisture over New Mexico, Kansas, Missouri. So there is some moisture that the computer's just not picking up right there, not actually plotting the moisture, showing it as color. Still looking at low level jet, 50 knots, 60, 65, 65 knots. I mean, you can say, yeah, that jet stream troughing right there, supporting that system. I mean, it's like I said, at this point, I'm not too impressed with it. I think it's weakened quite a bit. So I think it get even weaker as the sun goes down, and then see what we end up with. It's just going to move off, and then maybe getting absorbed into another low pressure system, or just dissipate and fill altogether. So we got that's 500 millibars. Go to 300. All right, we'll run a script for now on the 300 for moisture just to see what we got, and then we'll run the jet stream on 300, get a good idea of the wind. So now our moisture is pretty much just not even there. Let's run the pressure, isotherms, So we still got some moisture there. The computer's not picking up. So we can take that moisture all the way from Pennsylvania, Ohio, all the way up into Illinois. So that's not too bad. I mean, but it's not like majorly. I mean, 5 degree dew point depression is significant moisture, so can't rule it out. The low pressure system is basically just a trough at this point. You know, still indicating a low there. So let's see, we got southwest winds, northeast winds, northwest winds. So you do have some rotation there. That's, you know, you could almost close that low off. I mean, that is a pretty decent rotation. So for some reason the computer's just not picking that up. Which that's why I say these computer charts, they never do pick up every detail. You have to be able to look at that and analyze that yourself. Alright, so that's 300 millibars as far as moisture. Isotherms, I mean, they are crossing, the isotherms are crossing a little bit. We do have a little bit of cold air advection over Arkansas to the south a little bit, which that's just going to dry it out. So that indicates south, you know, the south part of that low is pretty dry. So 14 degree dew point depression, 20 degree. I mean, that's a pretty dry system right there. So cold air just rushing in and just pushing all the moisture out. So we'll go 300 millibar. We're still on 300. We're going to go with the winds. Let me erase this. And then we're going to pull up some wind, shade that in color, and see what this jet streams look like. All right, so we got a jet max over Florida and Georgia. So let me run pressure. And then we can run station plots along with that, and then that just gives us our wind directions and speeds. And here's our strongest winds right there over Florida. 100 knots right there over Florida. Look around Tampa. So there's the jet max. Winds out of the northwest. The jet, just a long wave trough in the jet stream. And then we got the jet max at the base of the trough. So that, moving into that system, that at that point is when this low pressure system starts to fill. When that jet max starts to move out of the long wave trough, and then you start typically getting the system start weakening and filling. So one more level up. Let's just go all the way to 200 and see if we have anything up there. I doubt we'll see any moisture. We'll run it just to see. I don't think there's any moisture in them levels. Nope, just way to the north. So really no significant moisture in the United States at 200 millibars. Let's just go ahead and run our winds. We can shade that. Another indication of the jet stream. Now our jet max. We have actually the jet max way over the Atlantic, but there's still pretty strong winds at 200 millibars over Florida. You're just over the Gulf, pretty much over the Gulf Coast. So with that low pressure system up over Tennessee, then, you know, let's go see what we got there. Let's look at our pressures. Let's see. That's just a trough. So just troughing right over Tennessee. There's, you got a cold, it's actually a little bit warmer, minus 52. So it gets colder as you go out. So a little bit warmer center on that low, just at that low pressure system. And then station plots. So winds out of the northwest, jet max to the south. There's 125 knots, it looks like. There's 110, 110, 15, 110. So that's your jet max at 200 millibars, which I think it's about 39,000 feet, something like that. It's pretty far up there. No significant moisture. Everything's dry. So that's pretty much it for the upper air charts. So, alright, give me a thumbs up, like my video, subscribe, keep track of the classes. The next one's going to be another class, and thank you for watching.